All right, here we are, SAT 22 for week 22. It is a student-produced response question, and let's take a look at it. The expression 6 times the fifth root of 3 to the fifth times x to the 45th power times the eighth root of 2 to the eighth times x is equivalent to a times b to the x, where a and b are positive constants and x is greater than 1. What is the value of a plus b? Well, how did we do on this question? Well, as you can imagine, most student-produced response questions, the answers are all over the place, as you can see here, range from 2 to something in the neighborhood of 2,000. Whoa! But there is one spike here at about 41% of people. The number's not indicated here, but it was 45.125. That was the correct answer here. And there's a couple of spikes right pretty close to that, maybe some rounding errors. And this, for the first time, is one that we rated a truly difficult question. So let's get to the bottom of the solution. And in order to start it, let's take a look at some properties of exponents, roots, square roots, or otherwise, and actually what does a root mean. So, for example, let's say that I have the square roots of 25. Of course, the square root of 25 is equal to 5, and the reason why is because 5 to the second power is equal to 25. All right, if I have something, I don't know, let's say that I have the cube root, a cube root of 8. Well, the cube root of 8 is equal to 2 because if I were to raise 2 to the third power, I would get 8 back. And of course, that's going to come into play as far as each one of these roots go. I have the 8th root, I have the 5th root up here. So in general, the nth root of x is equal to r if r raised to the nth power is equal to x. So that's basically the definition of the nth root. Okay, now it gets a little bit more complicated whenever you have negative numbers, and depending on this root, whether it's an even number or an odd number. Well, they completely threw that out the window because they said that x is greater than 1, and so we don't have to worry about x being 0, x being any kind of fraction, or x being a negative number, so it simplifies the problem somewhat. Anyway, so now let's take a look at some properties of roots. So properties of roots and exponents. So the first one is this. If I have the square root of, let's say, a times b, this is equivalent to the square root of a times the square root of b. In other words, you can break up these square roots, and it goes both ways. As a matter of fact, this is how we usually, one of the ways that we simplify square roots. And this would also work no matter what the index of that root is, if it's a third, square, fifth, eighth, or whatever. So as an example, if I have the square root of 50, I know that this is the square root of 25 times 2, which is the square root of 25 times the square root of 2, and the square root of 25 is 5, and the square root of 2 is left alone. This is how we would simplify, put in simplest radical form, the square root of 50. Okay, so that's going to come into play in here because we have to break up all of these roots. Now, we're also going to turn our expression, our radical expression with these roots here, into an exponent. And you can see I have to do that here because I have to make this thing look like some number a, some, who knows, could be an integer, could be a fraction or something like that, but it's some constant number a times x to just some exponent power here. So I have to, in some kind of way, turn all of these roots into an exponent instead. And this is how we do that. If I have the nth root of x, this is equal to x to the 1 over nth power. In other words, the square root of x is the same thing as x to the 1/2 power. The cube root of x is equal to x to the 1/3 power. Here, let me combine it. let's say that I have the fifth root of x squared. This is equal to x to the 2/5 power. Whatever this root index is, it becomes the denominator of the fraction. And now this is not just like some arbitrary rule. Let me demonstrate to you that this actually works. So, right over here, let's say that I have the square root of x. And I want to see what its exponent is actually supposed to be. So what I'm going to do is I'm going to pretend that this is x to some a power. And it's very similar to what this question is asking me to do. Okay, so if I had an equation and I'm trying to solve this thing for x and I have roots in it, what I do is the opposite of that root, actually the inverse of that root. This is square rooting, so I'm going to square both sides of this. So on the left-hand side, when I square the square roots, they cancel out as inverses and I just get x back. Over here on the right-hand side, I have a power to a power, and remember, a power to a power, you multiply those two exponents together. So this is x to the 2a power. Now, notice that, of course, that I have the same base. If I have the same base, that means my exponents must be the same in this equation. On the left-hand side, my exponent is an implied 1. Now, what I'm going to do is just equate these two exponents. Over here on the left-hand side, I get 1. On the right-hand side, I have 2a. And if I divide both sides by 2, I have a is equal to 1/2. In other words, the square root of x is the same thing as x raised to the 1/2 power. Okay, so let me pull up an image from the internet about some properties of exponents that might come into play. Like, for example, in this first one, if I have like bases, whenever I go to multiply, I add the exponents. Whenever I have the quotient of powers here, I subtract the exponents. Remember all of these from Algebra 1. Power to a power, I multiply those exponents together. Here's that negative exponent here. If I have some sort of negative exponent, it's just going to go down to the bottom. And anything to the 0 power is equal to 1. And here's the one that I was just demonstrating to you. And this is a to the x over y power is the wife root of a to the x power. Again, it's giving us a way to turn a root into a rational exponent. Okay, so now let's dive into the actual solution to whatever the heck is going on in this question. Okay, so I'm going to break up all of these little parts here. Actually, let me steal this and bring this further down the page here. Copy, and bring this down here. Yep. All right, I'm going to break up all of these little roots into individual little parts, and then at the same time, I'm going to use this little property which will allow me to turn all of the roots into exponents. Okay, so the 6 is going to stay, obviously, and then the fifth root, I'm going to turn this all into basically 3 to the 5th times x to the 45th to the 1/5 power. And then likewise over here, this 2 to the 8th x, all of this to the 1/8 power. Now, one of the properties of exponents, of course, that we just reviewed here is that a power, actually a product here, a product raised to a power, it's not a distributive property because a distributive property happens across addition and subtraction. This only happens as each one of these exponents is going to get multiplied times the 1/5. And over here on the second one, each one of these exponents is going to get multiplied times 1/8. So continuing here, I get 6 times 3 to the 5 over 5 times x to the 45 over 5. And then continuing with the one with the 8, I have 8 over 8 times x to the 1 over 8. All right, and now let's just continue to simplify here. Obviously, this 5 over 5 is to the first power, and likewise, this 2 to the 8th over 8th is going to be to the first power. And let me just combine all of these as basically the coefficient, the constant that's going to be right up front. So I have 6 times 3 times 2. Again, let me just kind of color these so that they kind of match up here. This guy goes with that. And then as far as the variable expressions go, For the first one, I'm going to have x to the 45 divided by 5 is x to the 9th. And of course, I'm going to give you some colors on that one to match these things up. And then x to the 1/8. Well, there's not much that we can do with this, so x to the 1/8 here. Okay, so multiplying up here, I have, this is 3 times 2 is a 6 times another 6 is going to give me a 36. And remember that whenever I have like bases, in order to combine these two things up under multiplication, I'm going to add the exponents together. So this is 9 plus 1/8. All right, let's continue to simplify here, and then we are almost done. So 36 will stay, x to the, and this is basically a mixed number. And this mixed number, you can turn this thing into a decimal if you want to. If you turn it into a decimal, it looks like this, 9.125 as an eighth. Or if you prefer, 36x to the, let's see, I would multiply 8 times 9 to get 72, plus one more is 73. 73 over 8. Either one of those. There you go. All right, we have now gotten this to the point where this is supposed to be equal to a times b, no, times x to the b power. And now all I have to do is, according to the problem, add my a and my b value together. So we can see here that our a is equal to 36 and the b is equal to 9.125. Now if I add these two things together, I get 45.125. Now here's the deal though. If we go back to the instructions, which are right here, it tells us that we only have 5 characters to work from. 6 characters if it was a negative number where the negative sign counts as one of the characters. Now, when we talk about characters, we're not necessarily talking about numbers because the decimal point actually counts as a character. So this is 1, 2, 3, 4, 5. So technically, your answer should be this. And you either do one of two things. You either round this appropriately, the 5 tells the 2 to round up as 45.13, or you can truncate. Truncate means you just chop off the rest of the decimals that you don't get to use, which is 45.12. Either one of these is the only thing that you could actually type into the Blue Book app if you're actually taking the PSAT or the SAT. But for the purposes of this, I took all 3 of these answers here. All right, well, I think that should conclude our work here. Bunch of properties of exponents, and if you took one thing out of this that's probably new, it's the fact that you can actually turn a root to some rational exponent.